What's up, everybody? So today we're going to continue on our discussion yesterday from the idea of light and what light is, and really kind of focus in on that tiny little sliver right in the middle that we called visible light. Okay, and today we're going to start looking at this idea of color. What is color? Why is it that we see certain things the way that we do? Okay, so first thing that I'm going to start off with is when we talked about sound, one of the things that I talked about was that sound is this imaginary thing in a true essence. Sound is just wiggles in the air that our brain perceives as, oh, those wiggles occurred, they vibrated my eardrum, I'm going to interpret those air wiggles as sound. And so that's why we get that idea of sound, is because it is our brain's way of interpreting these fluctuations and these vibrations in the atmosphere. Light and color are very much the same way. Okay? Light and color are just these amounts of electromagnetic radiation that as they pass through space, we have specialized hardware in our eyes that take that radiation, and we have special things on the back of our eyes, okay, rods and cones, and those are cells that will take that radiation, convert it into an electrical signal, and allow our brains to interpret that radiation floating through space as light and as color. Okay? And so let's take a little bit of a deep dive into what is color. Why is it that we see the things that we do, and what is it about the physical properties that we would utilize to better understand color? Okay. So first thing we should start off with is we took that huge long thing of, okay, so on one end we've got radio waves, and then more higher energy than that. We've got microwaves, and above that we've got infrared, and we got visible light, and we got UV rays, and we've got X-rays, and we've got gamma rays, right? We've got all those things, but today we're just going to look at that visible light right in the middle of that. And so again, just like with sound, just because we can't see it doesn't mean it doesn't exist. And there are other animals in the animal kingdom that have specialized eyes that allow them to see different frequencies, okay? So you have certain bugs that are really attuned to certain UV lights. You have other ones that are really attuned to certain frequencies of ultraviolet, and it kind of changes that spectrum of which they can see really, really well. Okay? But so for today, we're going to look just at what the human eye can see that we call color. Right? So if we look at one end of the spectrum, if we start over here and we have some of the lowest frequencies that our eyes can see, we see that color as red. Okay? And now if you think about the colors of the rainbow, this is just a situation where we have all the frequencies of light in order of lowest frequency all the way up to highest frequency. So if we start off here at the bottom, we start off with red, and then we go up a little bit more from that. Red, orange, okay, red, orange, yellow. Okay, then we get to green. Okay, and after we get to green, we go up to blue. Okay, now I'm going to stop right here because a lot of people, if you look at a textbook, will say that the order of colors goes red, orange, yellow, green, blue, indigo, and violet. Okay. For the purpose of today, I'm going to take indigo and violet and I'm going to squish them together. I'm just going to call it purple. Okay. Okay. And here's why. A little bit of history. So Sir Isaac Newton, he, again, talking about a dude that's like just ingrained in our textbooks. Sir Isaac Newton, when he was looking at color and really trying to understand a lot about light and color and prisms and all this other stuff, he was like, okay, well, I need to write down these colors from order of lowest frequency up to the highest frequency. And so he was like, all right, we got red, orange, yellow, green, blue. And he was like, you know what? In his time, there was something special about the number 7. Okay, if you look through a lot of scripture, if you look a lot of nature, if you look at all these other things socially, There was just something about this number 7. And so he felt obligated that when he was going to do this, he was like, you know what, I'm going to put 7 colors. Okay. So rather than just putting 6, red, orange, yellow, green, blue, and purple, rather than just having those 6, he was like, you know what, it needs to be 7. And so I'm going to take purple and I'm going to split it up and I'm going to call those colors indigo and violet. We don't need to do that. We just need to understand this idea of low frequency to high frequency and the colors that intermix between that. Because to be honest, we could break this up and call it 4 colors. We could call it 300 colors because it's all just a spectrum, and however we want to divvy that up is kind of, it doesn't matter. Okay. So these are all the colors, and these are the frequencies that are associated with each of these colors. Now, why is it that we see things for the colors that they are? A lot of people think that if you shine light onto something, whatever the color of the thing is what you're seeing. But interestingly enough, if I take this marker, okay, this marker right here, it is green. Most of us would say it's green, right? But the actual color of this is actually everything but green. Okay, so let's think about this practically. We have light that comes down. And if you notice, there's one color that there's 2 colors I didn't put on here. There's no white, there's no black. So what are white and black? Well, white is the abundance of all frequencies of light, and black is the abundance of none of the frequencies of light. Black is just an absence of color. Okay, so let's think about it. We got white light, which is all the different frequencies coming down. This thing right here that we perceive as green, we perceive it as green because the light comes down, it hits the object, and it actually absorbs a lot of that electromagnetic radiation. It comes down and it absorbs a lot of those colors, and it reflects off one frequency. It reflects off green. And so that green color comes down, it bounces off that, and it goes into my eye, into the rods and the cones in the back of my eye and your retina, and it sends that signal saying, hey, we just got some green. We're going to visually see that as green. So this object, as though we see it and perceive it as green, it's actually every color but green. Green is the color that reflected off of it and is the only color that this is actually not holding on to. Okay? So let me start asking some other questions. Okay? So if I've got this thing in white light and it's going to see green, okay, what if I reflect only green frequencies of light on this? What color am I going to see this as? Well, most of you would hopefully have the right answer and say that if I shine green light on this, it's going to appear green. Okay, pretty easy. Now, what if I ask you a question, what if I only shine red light on this? What color is this going to appear? I'm sure some of you are going to say it's still going to look green. No. Some of you are going to say it's going to look red, right? Shine the red light on it, so it's going to appear. No. It's actually going to appear black. Why black? Okay, well, let's go back to our thought right here. So if we've got white light coming in and it hits this, it's going to absorb every color but green and reflect green onto our eyes. Okay. If we shine green light onto it, it absorbs every color but green. There's no other colors other than green, so it doesn't absorb anything, and it reflects the green into our eyes. But now what if we shine only red light onto this? Well, if we only shine red light onto this, it's going to absorb every color but green. Is red green? Red's not green. So red gets absorbed, no green hits this, no green reflects, no green hits our eyes, and so we see this as black. So understand that the only way for us to see something is if there are frequencies of that light coming down and it hit an object, and that color has to be reflected off and get into our eyes. If this is, if we looked at this, if I shine red light, I see red. If I shine green light, I see black. Okay? So it's not that we mix those colors, it's just we have to have those frequencies in there, in that light, in order to see it. So what about transparent objects? Okay, what if we have, again, we have clear glass. Okay, well, that one's the easy one. All the light's going to hit it, and it's going to go through the process that we talked about yesterday, and it's going to make its way through, and it's going to get through. So all that white light gets through, so that's why clear glass looks clear. But what about green? What if we have green glass, or blue glass, or red glass, or some other color? Well, the interesting is, just like this appears green because it absorbs all colors and reflects the green. This would be an opaque object. If we have a transparently green object, it's going to, again, absorb all of the energy but green and only allow the green to pass through that. Right? So whatever color the transparent object is not because it changes the frequencies of light as it passes through, but it absorbs everything except for that color. And that is, it is conditionally allowing certain colors to pass through it. It absorbs everything else. Okay? And next, so if we look at the eye, okay, on the back of the eye, there's the retina, and there are these rods and cones that absorb that light. Okay, and that's what gives us vision. That allows us to see colors. Okay, so what we're going to have is we have certain colors that we see very, very vividly, right? Those yellows and those greens are very vivid to us. And that's because those cells that we have on the back of the eye are sensitive to certain frequencies. And there's certain overlap of those frequencies. And so we have those three different types of cells, those three different types of rods that as they get stimulated, if they're in a small little space on the back of our eye, they get stimulated and they send information to the brain saying like, hey, I got stimulated, that's green. Hey, I got stimulated, that's red. And if there's a certain amount of stimulation by multiple of those cells, they mix together, and that's what we get all these other colors, right? And so I just want you guys to understand that the reason we have something those vivid, those yellows and those greens, because there's a lot of overlap with these middle colors, okay? As we get to the outskirts, the reds, we get the outskirts to the deep purples, those are ones that there's not as much overlap from these cells, and so our brain doesn't process them as vividly because we don't have as much information from the eye to be like, yeah, it's this color because we had a bunch of cells that all agreed that it was this color, whereas those greens and yellows, we have a lot of overlap with that. Okay. All right, and the last thing I want to talk about here with color and color theory is when you are in an art class and they start talking about, hey, we're going to mix this color and this color, and we're going to get a third color. Those are pigments. Those are pigmentations. And again, because something blue and something yellow, they mix together and it appears green because the inherent structure of that material changed. And it's now going to change what is absorbed and what is reflected. Okay? That is different than how we will describe colors in a physics class. In physics, we are going to talk about the light color. Okay, we're not talking about the pigment of the stuff that we're doing. We're talking about the color of the light. Okay, and I want you guys to understand that if we start looking at mixing frequencies of light, that will actually change what we perceive, and it's different than mixing pigments of paint or markers or whatever else it is that you're looking at. So we've got a series of colors that if we mix, our eyes perceive them as different things. So some examples we have, if we mix blue and green, we get a color called cyan. It's like a light blue. Okay, and you might be like, that's weird, right? Green and dark blue, dark green, dark blue make light blue. We can mix red and green and get yellow. And it's not that it's changing the frequency to yellow, but again, it is how the brain perceives those mixtures of those colors. If I've got one cell right next to another one, this one picks up the red, this one picks up the green. our brain processes like, oh, those two together, they're gonna look yellow. It's gonna look yellow, but there's no yellow color. It's just the way our brain processes the mixture of the light within something. Okay, and this is one of the reasons that the screen that you're watching me on right now, you can see all of these colors, but it is actually only transmitting 3 colors: red, blue, and green. And it is mixing how much of each of those 3 colors together to give you this wonderful array of all these different colors that you could be seeing, because it is tricking the eye and mixing these colors together, these colors of light together, to give us the whites, the blues, the blacks, the yellows, the greens, all of these colors together to give us this spectrum that we see. Okay? All right, that's everything I wanted to get through today with color. As we're kind of shifting closer and closer to the end of this course and this unit, we will continue on. Next, we will talk about how light is emitted from something, and then finally looking at how things are reflected and how they are bent as they travel through something such as a lens. All right, that's it for today. I'll talk to you guys later. Bye.